Radioactive decay is a phenomenon that actually follows exponential decay. So it turns out that radioactive materials decay so that after a fixed amount of time, a constant proportion of the initial radioactive material will have decayed. So in other words, if you wait for a day and 10% of the radioactive material has decayed away, when you wait for another day, 10% of that will have decayed away, and so on. So for example, suppose we have a 10-gram sample of iodine 131 that is polluting a field. The half-life of iodine is 8.07 days, it turns out. So after 8.07 days, half of the iodine will have decayed away. Let's find a formula for the mass of the iodine remaining after t days, and let's use that to figure out how long it is until less than a milligram of iodine remains. Maybe we need to wait for there to be less than a milligram of iodine 131 just to make sure that the field is safe to use for crops, I guess. So let's see, we know we're starting with 10 grams, so since this follows exponential decay, we can write, for f of t, we know we can write ae to the kt. Okay, but we have an initial value, so we know that a is 10, and this is going to be in grams. And also, this half-life is telling us that if we wait the half-life, so 8.07, half of the initial amount is left, so that would be 5. So f of 8.07 is 5, but now we can plug this into our formula. So we know a is 10 times e to the, we don't know k yet, so k times t, but we're plugging in 8.07. Okay, and now we have an equation that we can solve for k. So let's divide both sides by 10. We get 1/2 equals e to the 8.07k. Notice that this half is here because we want to know how long until half is left, or because 8.07 days is how long it takes for there to be half the amount that's left. So really, you know, we could have jumped directly to this equation, I guess, is what I'm saying. All right, now take natural log on both sides. So natural log of 1/2 is 8.07k, and then we can divide both sides by 8.07. And we get that k is, let's see, so natural log of 1/2 divided by 8.07. So that's negative 0.08589. And the fact that this is negative is what makes this exponential decay, right? Because this k value is negative. Okay, so that means that our function is 10 times e to the negative 0.08589 t. And we want to know, when does this get down to a milligram? A milligram is a thousandth of a gram, so 1/1000 equals 10 e to the 0.08589 t. And now just solve for t. So divide both sides by 10. 1/10,000 equals e to the 0.08589 t. Take natural log on both sides. Natural log of 1/10,000, so that's 10 to the -4th, yeah, equals, and then natural log on the right hand side is 0.08589 t, and then divide to find t. So get the decimal approximation. Let's see, natural log of 1/10,000 divided by, oops, I dropped a minus sign. There should be a minus sign here, here, and here. So now divided by negative 0.08589, and I get 107.23. So this is going to be in days. So if this iodine showed up in your field, you'd have to wait a third of a year, I guess, almost, until you can start using that field again. For another example, let's suppose that a lab starts with a 50-gram sample of sodium-24, and after 1 hour, there's only 47.742 grams of sodium-24 left. What is the half-life of sodium-24? So remember, the half-life, that's how long it takes for there to be half of the remaining amount left. So what we want to know is, how long does it take until there's only 25 grams left. Well, to solve this equation, right, we know that this function is going to be a times e to the kt. Before we can solve this equation for t, we're going to have to find a and k. Right? Fortunately, we can do that because we know how much we start with, and also we have this data point. After 1 hour, we know how much is left. So we'll be able to find a and k. So let's do that first. A is the initial mass of our sample, and that's 50 grams, so there's no solving to do there. But to find k, we have to use this data point, right? After 1 hour, there's 47.742 grams left. This is giving us a data point, so we can plug this into our function, right? We know that f of t is 50 times e to the kt, so we can plug in this data point. We get 47.742 equals 50 e to the kt, and now e to the k times 1, right, because t is 1 here. So now divide both sides by 50. 47.742 over 50 equals e to the k. Now take natural logs. We get natural log of 47.742 over 50 equals k. All right, so now we can get a decimal approximation for k. So we're taking natural log of 47.742 over 50, and k is about negative 0.0462. Okay, now that we know k, we can come back and use this function f of t, which is 50 times e to the negative 0.0462 t. We can use this to figure out how long it is, what the half-life is, because we can just set this equal to 25. Divide both sides by 50, and we get 1/2 equals e to the minus 0.0462 t. So you can see that it doesn't actually matter how much we started with. That won't change what the half-life is, because right, whatever you start with, you put half of it over there and then divide by what you started with, you're always going to end up with a 1/2 right here. So it doesn't really matter how much you start with when you're finding the half-life. So now take natural log on both sides. So natural log 1/2 is minus 0.0462 t, and then we can divide by negative 0.0462, and we'll get our half-life. So natural log of 1/2 divided by negative 0.0462, we get just about 15 days, a little bit more. So the half-life of this material is 15 days. No matter how much you start with, if you wait for 15 days, half of it will be gone.